Okay, we're going to talk about something called the first derivative test. So, last week we spent pretty much all that time analyzing derivatives and focusing on setting the derivative equal to a number to find c values, right? But that's all it was. We didn't really do much to interpret them except for the mean value theorem. So, here's what we're going to do we're going to use it for the first derivative test. And the first derivative test is just this. Let c be a critical number of a function f that is continuous on an open interval I containing c. If f is differentiable on the interval, except possibly at c, then f of c can be classified as follows. If f prime of x changes from negative to positive at c, then c has a relative minimum at c, comma, c of f, or f of c. If f prime of x changes from positive to negative at c, then f has a relative maximum at c, comma, f of c. If f prime of x is positive on both sides of c or negative on both sides of c, then c of f is neither a relative minimum nor a relative maximum. Okay, that's a lot to take in, so pause the video if you need a moment. But I'm going to show you what I mean with this example of f of x is x squared minus 4 quantity raised to the 2/3 power. This has a lot of things going on, so be patient. So the first thing they talk about is that I need to have a continuous function, which I do. It's not pretty, but it would be a continuous function. If not, pause the video, go to Desmos, type that in, look at that graph, and tell me that's not continuous. And the second part that they mention is if f is differentiable on the interval except possibly at c. So remember that c is a critical number, and a critical number is an input that would make your derivative equal 0 or make it undefined. So that's why they're saying that f could be differentiable on the interval except possibly at c, because what if it's not, because the c value could be a critical number where the derivative is undefined. Okay? So let's get started. The first thing I need to do is I need to find my critical numbers, which, again, where my derivative will equal 0 or where my derivative is undefined. So doing some math, we get f prime of x would equal the power rule right here. Putting that chain rule to work. Boom. So then cleaning that up, I could say that f prime of x equals 4x over 3 times x squared minus 4 to the negative 1/3 power. All right, so that means that f prime of x equals 4x over 3 times x squared minus 4 to the 1/3 power. Okay. So I have my derivative. So to get the critical numbers, I need to figure out when this will equal 0 or when this will be undefined. And I need more room. So because I have a rational expression now, rational expressions equal 0 when the numerator is equal to 0. So to get this part, I just really need to figure out what's going to make the 4x equal 0. And I realize that x is equal to 0. So that's one possible value of c. And if I'm trying to figure out where it's undefined, well, again, it's a rational function, so I need to figure out where the denominator would equal 0. And the only way this is going to be equal 0 is if ... the x squared minus 4 is equal to 0. So possibly at positive or negative 2. And if you have questions on how I did that, just pause the video. Take the time to solve it out to prove it to yourself. All right. And again, these are values of C. These are my critical numbers. So I'm going to go back and read over what it is saying for the first derivative test. Okay. If f prime of x changes from positive to negative, if it changes from negative to positive. Okay. So, okay, let's talk about what this means. So, if we are discussing the derivative, remember the derivative is the instantaneous rate of change, aka the slope of a point. So here's another little thing we want to consider. If f prime of x is positive, then f of x is increasing. Which makes sense, because if I have positive slopes, then my graph should only be going up. All right. And I also want to consider the opposite actually. If f prime of x is negative, aka less than 0, then I would be able to say that the original function f of x would be decreasing, because again, that would mean that I have negative slopes, and negative slopes means that my graph is going down. Okay? So your derivative could possibly be positive, it could be 0, or it could be negative, or it could possibly be undefined. So I'm going to make a little line to help me figure out what's going on with my function here, f of x is equal to that. Because again, it's all about the derivative. If I can interpret the derivative, then I can talk about what's going on with the original function. I can tell you if the original function is increasing, decreasing, or if it has a relative minimum or a relative maximum, aka the relative extrema, just by interpreting the derivative. So here's what we're going to do. I have three critical numbers, right? I had 0, -2, +2. That's it. So I'm going to make myself a little number line. And this is going to be a little bit of a throwback to your integrated 3 math. Right? So I know that if I put my critical numbers on the number line, I should have a -2, I should have a +2, and I have 0 for my critical numbers. And I need to keep track of what my derivative was. So if I'm not mistaken, my derivative was 4x over 3 times x squared minus 4 to the 1/3 power. Okay. So I know that if I plug in a -2 or a +2 into the derivative function, I would get something undefined. So I'm going to put a u there to represent that undefined. If I plug a 0 in for x into my first derivative, I know that's going to get me a 0 because that's how I got it to begin with, right? But aside from those three values, I do not know if my first derivative will be positive or negative or either. So I need to test out the 4 different intervals. So I'm going to pick a number that's less than -2, and I am strategically lazy, and I'm going to say -3. So my first derivative at -3, if I plug that in, 4 times -3 gets me a negative number, right? Over, if I plug a -3 in for the x, I get 9 minus 5. I'm sorry, 9 minus 4, so that's positive. So I'm going to get a positive number in my denominator. If I needed to help yourselves out, go ahead and actually evaluate f of -3 and tell me what number you end up with. But just by doing this little bit of analysis of thinking about how the operations play out, I can say this will be negative. So that means everything less, for all x values less than -2, I will have a negative slope, which means I should have a decreasing function on this side. If I go and pick out another number between -2 and 0, and again, I'm going to be a little strategically lazy and say -1 because I want to keep nice numbers. If I replace the -3 with a -1, if my computer cooperates, okay. Well, 4 times -1 will get me a negative number up top. And 3 times a -1 squared but -4, that'll also be negative. So I'm going to say I should get a positive number, positive slopes in here. So I can say my graph will be increasing between -2 and 0. And again, a little strategically lazy. What's a good number to use? Number color. I'm going to use 1, right? So replace everything in here and update it to if I use a positive 1. So 4 times 1 would give me a positive 4, so I have a positive number up top. 1 squared minus 4 would still be negative. The cube root of that would still be negative, and multiplying 3 by that negative still makes it negative. So right here, I know I'm going to get negative, so I can say between 0 to 2, I have a decreasing interval because all the slopes would be negative. And if you're not sure, then just pick out different numbers aside from 1 to prove it to yourself. All right, last but not least, what color have I not used? Yeah, let's go with, no, I already did red. Yellow. So I'm going to use a positive 3. So update here to put it at positive 3. So if I plug a positive 3 in for the x, I would get a positive 12. If I plug a positive 3 in for the x, that would give me a, well, actually I should put underline. I don't want you guys to think I'm putting zeros in. Positive 3 in there, that's 9. 9 minus 4 is positive. Cube root of a positive is positive. 3 times a positive is positive. So there's also positive. And if you divide positive by positive, you get positive. So that means in this interval, it's increasing. Now I know it's a lot to look at, so I'm going to get rid of some stuff to try to clean this up and show you what I mean. So, based off all the little calculations I did for my first derivative, I have this number line right here. So you have to consider when calculus was made. This was in the late 1600s, early 1700s, and perfected all the way through. People do not have the technology that we currently have. If they wanted to see what the graph of f of x looked like, they had to consider when is it increasing, when is it decreasing, where do I have max or mins, right? We don't have Desmos or our T83 calculators or T84s, whatever, to make that graph. They decided to just reason it out and think about what would have to be true, and that's where this number line comes in from. That's the purpose of this, to do that like function analysis. And I know that we have calculators that can do this, but it's important to consider the analysis that we can pull from this. All right. So if I think about this right here, and I'll show you some of the graph sketching, curve sketching, I should say, that you can do with just this piece of information, you'll see. Jump cut. So I was able to clean this up and give myself more room. We have the original function f of x there. So now, based off this, I can provide some sort of sketch for what I think this graph should look like to help me make sense of what the conclusions of first derivative test is trying to get me to get to see. So I know that based off my critical numbers at those values, I'm expecting special stuff to happen, right? I'm expecting maximums and minimums possibly to occur. So I'm going to go ahead and make note of that. Negative 2, 0, and positive 2. So at those x values, I'm expecting some sort of extrema. But I need to figure out exactly where those are. So I need to figure out f of negative 2, f of 0, and f of positive 2. So notice I'm going back to the original. The first derivative tells me if I should expect the extrema. The original function tells me where exactly that coordinate point would be. So that's why I plug it back into the original. So if you do that real quick, you should realize that you get 0, you get 4, pause. Sorry, I paused the video to check my math. You actually get the cube root of 16, which is somewhere between 2 and 3, because 16 is between 8 and 27, the two perfect cubes there. And if you plug if you plug a 2, you get 0. So if I make these into coordinate points, you get 0, negative 2 comma 0, you get 2 comma 0, and you get 0 comma cube root of 3. All right. So this part with the graph sketching, like this right here, I'm doing for your sake so you can see how to interpret your first derivative. So all I know is that in this interval right here, my first derivative was negative, and I'm saying should be decreasing. So I don't know how exactly, but my graph should be decreasing. I can make an educated guess because I've seen radical graphs before, so it might look maybe something like this. I don't know, but it's decreasing. Then it stops. And then over here in the purple area, I see that this is now increasing. So now from here, it's starting to go up. And it continues to increase till I get to that point. Then I get 0, so I get a horizontal tangent line right there, because that's what it means for your derivative to equal 0. Fun fact. Then I go to the orange, and in between this interval of 0 and 2, my graph should be decreasing, so decreasing until I get to that point, okay? And then from this last part where it's anything great, when your x values are greater than 2, it should be increasing. So that is kind of what my graph could look like. Just a general sketch by just knowing the derivative should be positive or negative. So now let's look back at the wording. And by the way, if you're looking at the textbook, the first derivative test is on page 180. So it says, if the derivative changes from negative to positive, you should have a relative minimum. So let's go ahead and document that I have a relative minimum. So I went ahead and I identified each of the, for each x value that turned out to be a critical number, and I got the coordinate point, so I knew where it would be on the graph. I went ahead and classified them as relative maximums or minimums according to the first derivative test. So I'm going to highlight, hopefully, this part of the graph was decreasing, as was this one. And this part of the graph was increasing, as was that one. So when you go from decreasing to increasing, that's where we get that relative minimum, because it's going down and it bottoms out, then it starts to come back up. Then your graph is increasing, so it's going up, it maxes out, then starts to decrease. As you're decreasing, you bottom out, and then you start to increase again, right? That's all the first derivative test is trying to get you to view and look at using calculus, understanding the fact that the derivative is really just talking about the slope. That's it at its core. And this is a more complex example. So if you're okay with this right here, you should be fine for the assignment. And if not, ask questions during our live Zoom meeting on Monday. Have a good break. Or breaks. It's the weekend. Have a good weekend.